Now this is an introduction to the graphs of logarithmic functions, and I will start with the population model. So suppose I have a population at time t is going to be in years, and the population is 100 initially, and the model is the following. This is 2 actually, so e to the 0.02t. Now recall maybe e is a special number, but it's often used in those models. So e is 2.71 something. Okay, it's an irrational number. And so p of t is 100, e to the 0.02t. So when t is 0, this is going to be 0, and e to the 0, like any other base, is going to be 1. So that's why p of 0 is 100. It's the initial population. So when the population at time 0, so initially, is going to be 100. So that's the 0, 100 is going to be our y-intercept. So often we call that point 0 p subscript 0. So the p naught or p0 is the initial population. And then it's growing exponentially, and maybe to convince you of that, maybe the 0.02t in the exponent throws you off, but we can use a trick from exponents just to rewrite that as 0.02 to the t. So recall that when we do that, like if I do a to the y to the x, that's equal to the ax times y, so the exponents will multiply each other. So that's why I can write it that way. And e to the 0.02, I can just type that into my my calculator, and we'll see that it's approximately 1.02. Okay, so you can see it this way. So this way we have a function that's of the form a b to the t. So that's exactly what a logarithmic function is like, and we've seen an exponential function is like, and we've seen the graphs of those functions. And here b is above 1, so that's why it's going to go up. Okay, it's going to be increasing. Okay, so here b is greater than 1, so that's going to make the graph of the exponential function go up like that. Okay, and 1.02, you can also think of it as 102%, or you can see it as 1 plus 0.02, like that. So the 0.02, if you recall our exponential models, it's responsible for the growth. So each year the population will grow approximately by 2%. So that means that's approximately 2% of increase in the population each year. So this is all about exponential functions and an application to population growth. And where's the does the logarithm come into play? Well, so this is t and p. So suppose instead what I'd like to do is, instead of having population as a function of time, I'd like instead to have for a given population, how much time it takes to get how much time it takes to reach that population size. Okay, so we know that, for example, when t is 0, so initially population is 100, right? So we actually see that the 0.0100 that was on our graph initially is now going to be on the x-axis at 100 and 0 on the graph of the other function I'm looking for. So the function I'm looking for is the following: is what function, and I want a formula. So when I say what function, I want a formula for that function, would describe the time it takes for a population to attain a certain number. Okay. So once again, the idea behind this is that initially on my first graph, I'm giving time, and with Time value, I can decide what the population is, but now I want to go backwards. I want to know what the time is given a population size. Okay, so in some way, what I want to do, like this is function p that outputs population. What I want is the inverse function of that population function. Okay, so we need to find the inverse of p above. To find the inverse of p. And this is where logarithms come into play, because you'll recall that logarithms are the inverse of exponential. The inverse function of p. So answering that question sort of backwards will bring into play the inverse function of my exponential function, and this is how I'm going to get a logarithm. So what I'll do here, I'll write what p is as a function of t. Okay, and so normally, right, we have y as a function of x. So you're used to having it written like that, but you have to be able to do the same thing with other types of variables. And I know that's often like we'll switch around the roles of x and y and solve for y. Okay. That'd be a way, but the thing is here, I don't want to see, because if I do this, I'll again have y as a function of x in the end, and I don't want to have here p as a function of t in my other graph. So in my other graph, I really want to interchange the roles of t and p and leave it that way. It's as if I have x and y here, and really I want to have x sort of on the vertical axis and y on the horizontal axis in the end. Okay, so I want to keep my I really want to invert the variables. So what I'll do here is I'll just solve for t. Okay, so let's solve for t. In this way, I'll have t as a function of p, which is exactly what I want on my axis here, right? T is a function of p. So that's exactly what I want. So let's erase this to make some space. Now to solve for t, we're going to divide by 100 on both sides, like that. And now we've got an exponential equation, okay? To bring in the logarithm, I'm going to write that equation as a logarithmic equation. Okay, so a log is an exponent, right? So this, okay, is the exponent. So 0.02 t is the exponent, so it's the log, to which we raise e, so it's log in base e, in order to get p over 100. So that's converting that into a logarithmic equation. And log in base e, you'll recall that it has a special name. It's called ln of p over 100. So there's actually a button or a calculator, ln. It calculates logs in base e. And finally, to solve for t, I need to divide by 0.02, like that. But 1 over 0.02 is actually 50, because it's 1 over 2 over 100, or 1 over 1 over 50, so that's 50. So finally, this is our function. So this is how t is a function of p. So if you can, maybe to emphasize this, t is now a function of p. So time is a function of population. And this is what we'd like to graph above. So what we need to do to graph the inverse function is draw the line p equals t, or the line y equals x, but here x and y are called t and p, and then reflect that across the across this axis. So we're going to get something that looks like this. Okay. So that's going to be a graph of our function. So I'll just actually add it below here. It'll look better. So it starts again at 100, 0. Because when t is 0, population's 100, and then it just goes up like that. Okay. And that's what the function would look like. So of course here I'm interested only in positive values of t, but if I would be interested in negative values of t as well, I could extend this inverse function and have this part here, and the t-axis would be an asymptote. Okay, the reason for that is that for our exponential function, the t-axis is an asymptote, and as you reflect that, so this line, this t-axis, which is the asymptote, as you reflect it across the line p equals t, it becomes the p-axis. So this plunges down all the way to minus infinity like that if we extend it. But here normally in this problem we're just interested in the top part, the part where t is positive. Okay. And we can answer some questions with this. I could answer like a question like how many years before the population doubles? Okay, so how many years before it doubles? Well, that means we want to go from p, let's say, equals 100 towards p equals 200, right? That'd be doubling the population. So we want to know how much time it takes to do that. Okay, so here we can answer this with our t function. We just have to plug in the new population that we want. We want 200, and we're gonna get how much time it takes to do that, to double the population. So that's going to be 50 ln of 2. I type that into my calculator, and it's going to give me 34.7 years. Okay, so that means that to get to a population of 200, okay, it takes us to 34.7 years approximately. So this point here on the graph is 234.7.